In this video, we're going to discuss the binomial theorem, which is associated with a particular kind of series, specifically the series we get when we expand a binomial raised to a power and look at all of the individual terms that result. So let's look at a couple of simple series that we would get when we raise a binomial to a power, and then we're going to generalize what happens for any power. So when we find the binomial expansion of something like a plus b squared, we have the following. Now, of course, we know, first off, we cannot just square a and square b and add them together. Squaring means literally multiplying something by itself. So when we look at an expansion of one binomial times itself, we know, of course, that represents not only two multiplications, what we would get from just squaring each term, but technically four multiplications. And so we multiply our first pair, which results in an a squared. We multiply our outer pair, which would give us a times b. We multiply our inner pair, which would give us b times a. And we multiply our last pair, which would give us b squared. And of course, the two terms in the middle are technically like terms, even though they're rearranged. Multiplication is commutative. Doing multiplication in either order does not change what we're actually looking at. So we combine those two terms together, and that's going to give us a squared plus 2ab plus b squared. And so that is what we refer to as the expansion of this binomial raised to the power of 2. Now, what if we wanted to expand a plus b cubed? Well, an easy way to do that based on what we already know is to just take a plus b and add it to what we already got when we took a plus b and squared it. So in other words, multiply it by a squared plus 2ab plus b squared. Now this represents a total of 6 multiplications. So the term a needs to distribute to the 3 terms, and then b needs to distribute as well. So for our first one, we have a times a squared, which will give us a cubed. Now we can multiply everything a, or we can go a and b one at a time. I like to just start with a and distribute that and then go b. So a times a squared is a cubed. A times 2ab would be 2a squared b. And then a times b squared would be a b squared. Then we do the same thing with b. So b times a squared. So plus b times a squared. B times 2ab. So plus 2a b squared. And then b times b squared, which would be b cubed. And again, we have 1, 2, 3, 4, 5, 6 terms because we get 3 terms from distributing a and 3 terms from distributing b. Now, just like with the previous problem, we have some like terms. They may be disguised, but they are like terms. So a cubed and b cubed, those are solitary. They don't combine. They're not like terms, and there's nothing else that they combine with. Now, 2a squared b, notice there's another term that has an a squared and a b. So we have 2 of them plus another one. So a cubed plus 3a squared b. And then we also have ab squared and another 2ab squared. So plus 3ab squared plus b cubed. So these would just be the expansions that result when we square or when we cube the binomial a plus b, which is completely generic. So keep in mind, if we were to sub in different values in place of a and b, our expansions would be structured in this way, just with a different value of a and a different value of b. So several different patterns start to arise if we continue expanding powers of the binomial, specifically a plus b to the n power. So one pattern we'll see is that the exponent on a will decrease on sequential terms as we go from left to right, and the exponent on b, excuse me, that should be decreases, and the exponent on b increases. So we actually see that in both cases. So for the first expansion, we start with a power of a, so a squared, and then we go down to a to the first power, and then on the last term a disappears, which means you could think of it as being a to the 0 power. Well, on the first term we don't have a b, so that would be b to the 0 power, and then b to the first power, and then b squared. So the powers of a decrease, and the powers of b increase as we work our way left to right. Same thing here, so a cubed, and then a squared, and then a disappears, and then b is no longer there, but then it appears, so b to the first power, and then b squared, and b cubed. So this pattern with the exponents that we see would continue if we continued to find additional powers of this binomial. Now also the degree of each term, in other words the sum of the exponents, is going to be n, whatever the exponent is associated with the expansion. So a cubed, we have a degree of 3, a squared and b to the first power, 2 plus 1 is 3, a to the first power b squared, 1 plus 2 is 3, and then b cubed, again a degree of 3, same thing for a plus b squared. And then also the number of terms, there's a pattern there, so the number of terms in each expansion is going to be n plus 1 once we combine together all of our like terms. Now the other pattern that we don't necessarily recognize initially in terms of just what is the pattern, what's actually happening as we go from one expansion to the next, is what's happening with the coefficients as n increases. So in other words, the coefficient as we work our way across our terms left to right. So if n is 0, then we will have just a coefficient of 1. Anything to the 0 power is just 1. So we're just going to have a 1. Now if we were to raise our expansion to the first power, a plus b to the first power means we're just multiplying it by 1. There's nothing there, it's just itself. So we'd have a coefficient of 1 and 1. Now if we square, we saw these coefficients, so we had a 1, a 2, and a 1. So 1, 2, and 1. Now when we cubed, we had a coefficient of 1, 3, 3, and then 1. So 1, 3, 3, and then 1. And so we start to see a pattern emerge in how the numbers in one line relate to the line before it and relate to the line after it. So if you take any pair of numbers, then the resulting value between them is going to be their sum. So along the outer edges we just have 1s, but 1 plus 1 gives us 2, and then we see the same pattern on the next row. So 1 plus 2 gives us 3, 2 plus 1 gives us 3. So if we were to follow the same pattern on the next row, notice we'd add on one more value. So 1 value, then 2, then 3, then 4, then 5. So 1 on the outer edge, and then sum the two values above, which would give you a 4. Sum those two values, which would give you a 6. And then 3 plus 1 would give you 4. And then we also have a 1 on the end. So not only are we summing pairs of terms, but notice there's also going to be some symmetry involved as we go from left to right across the row. And the same kind of pattern would continue if we kept going. So this particular array of numbers arranged in a triangle has a name. It's called Pascal's triangle. And this triangle is going to be important because ultimately it gives us the coefficients associated with any binomial expansion that we want to evaluate. So suppose we wanted to find a plus b to the 4th power using the triangle. In other words, we're looking at the row we just generated at the very end. So using the patterns that we've recognized already, plus that last row in the triangle, we can actually expand a plus b to the 4th power without needing to manually distribute terms. So first off, let's look at the terms and then the powers. So we go from a with the highest power decreasing down, and then b, powers of b will increase as we go across. And let's leave a little bit of space so that we can add in the coefficients. So for our first one, we have a to the 4th power. And then for our next term, the power on a is going to decrease, and then the power on b is going to increase. Well, we don't have a b to start with, which means suddenly b is going to appear. So it's b to the 1st power. And we can always check by making sure that our degree per term is the same. So the degree should add up to 4. So here we have a degree of 4. 3 plus 1 is 4. Okay, and then we're going to decrease our exponent on a again, which would give us an a squared, and then increase the exponent on b, which would give us b squared, plus next term, so a decreases, so a to the 1st power, and then b increases, so b cubed, and then our final one would be b to the 4th power. So those would be our powers of the individual terms joined together to generate our n plus 1, which is in this case 5 terms, but we also need their coefficients. So the coefficients are going to come from the row in Pascal's triangle associated with our value of n. So when n is 4, we have coefficients of 1, 4, 6, 4, and 1 in that order. So 1 times a to the 4th power, 4 times a cubed b, 6 times a squared b squared, 4 times ab cubed, and then 1 times b to the 4th power. And of course, if we want to clean that up, that's going to be a to the 4th. We don't necessarily write a coefficient of 1, plus 4a cubed b, plus 6a squared b squared, plus 4a b cubed, plus b to the 4th power. And so notice in some ways that's a pretty major time saver, particularly if you didn't already have the preceding expansions for a plus b squared, a plus b cubed, and then so on and so forth. So it's just a matter of how are the exponents exhibiting a pattern, and then how are the coefficients exhibiting a pattern as well. Now, directly using the triangle for higher powers would be cumbersome because we have to generate each of the preceding rows. So in some ways, generating Pascal's triangle looks kind of like a recursive sequence. Each individual row will factor into the row below it, will factor into the next row. So for instance, if we wanted the 100th row, we'd need the 99th. Well, that would require the 98th, and then so on and so forth all the way back to the very first row. So using the triangle for larger expansions is not going to be ultimately a majorly realistic thing to do, just because we'd have to have every preceding row. We can't just immediately pick out what the values would be in the row that we want. Fortunately, we also have a formula, think of it like a formula for the nth term in a sense, that allows us to compute what we call binomial coefficients directly. So the values that we get from Pascal's triangle are referred to binomial coefficients, not surprisingly, because they give us the coefficients that result when we raise a binomial to a power. So we're going to let n and r be non-negative integers. So in other words, 0 is the lowest value they can take on, where n is greater than or equal to r. So the expression n over r, which we read as n choose r, is called a binomial coefficient. It expresses the relationship that generates these values, 1, 4, 6, 4, and 1, and then all of the subsequent values as well. And it's defined in the following way. So it's going to be n factorial divided by r factorial times n minus r factorial. So whatever that value comes out to, that value represents a binomial coefficient. Now in some cases, as opposed to n choose r, you'll see the value NCR. You'll see that notation used instead. And you actually have a shortcut in your calculator to evaluate something like this. So we'll do a couple by hand and then I'll show you where the button is in the calculator. The button in the calculator is going to look like this. It's going to look like NCR. So let's evaluate the following, and then we'll compare the values we get to that expansion we just found. So 4 choose 0, and let's calculate this one directly using our formula. So 4 choose 0. Okay, so our numerator will be n factorial, which is our upper number, factorial. So 4 factorial. And then our denominator will be r factorial, which is 0 factorial, times n minus r factorial. Well, n minus r is going to be 4, so 4 factorial. Well, immediately we see a common factor in the numerator and denominator, so that eliminates. Now, initially it looks like maybe we're dividing by 0, which of course would be a problem. But if you remember, when we defined factorial, 0 factorial was defined as being 1 for this very reason. So in our numerator we have a 1, and then 0 factorial in the denominator also evaluates to 1. So we have a value of 1. So 4 choose 0 is 1. Now what about 4 choose 1? So let's do this one directly as well. So our numerator is going to be n factorial, so 4 factorial. And then our denominator is going to be r factorial, so 1 factorial, times n minus r factorial, which would be, in this case, 3 factorial. Well, we can again do this in the calculator, but we don't need a calculator. We've talked about how you would simplify something like this. So remember, the larger factorial actually contains all of the multiplications below it. So 4 factorial contains 3 factorial as part of it. And we can see that by pulling off just individual factors. So if we pull off just a 4, then we're left with 3 times 2 times 1, which is also known as 3 factorial. And then of course we still have our 1 factorial, our 3 factorial. And now we see that common factor, which divides out. And so in the numerator, we're left with 1, and then in the denominator, 1 factorial, which is also just 1, and so we get a 4. Okay, so that would be the method we would use to evaluate these by hand. So now let's talk about how you would do this in the calculator, because again, the calculator will do this for you. So in place of 4 choose 2, you're going to look for 4C2 in your calculator. So there are a couple different ways to evaluate this, and it's going to depend on how new or how old your calculator is. So if your calculator is newer, let me show you how to do that first. So you're going to go to the Math menu in your calculator, and you're looking for PROB, which stands for probability. So we're going to go to the probability submenu, and you'll notice that option 3 is NCR, and that's exactly what we want right here. So I'm going to highlight that, and I'm going to press enter, and notice it gives me a box to type in the first value and a box to type in the second value. So I'll type in my 4 for the first value, and then I'll use my arrow to go over to the second box, and then I'll type in my 2. And then of course I can hit enter, and that's going to give me the value 6. Now if you have an older graphing calculator, you can still do this. You'll still find that C operation in the same location, but how you type is going to be a little bit different. So as opposed to going and finding the operation first, you need to start by typing your value of n. And technically this works for this version of the calculator too. So you'll start by typing a 4, and then you're going to go into the Math menu, and then go to probability, and then choose NCR, and then you'll get what you need. So notice in this case, it automatically understands that 4 is supposed to be the first value associated with C. But again, if you have an older graphing calculator, you will absolutely need to do this first. And then, of course, you can type your value for R, and we know that comes out to 6. So that is going to be the value for 4 choose 2. So let's do the last two as well. So we want 4 choose 3. So 4, then Math menu, then probability, then NCR, 4 choose 3, which gives us 4. And then 4 choose 4, so 4C4, so 4, and then Math menu, and then probability, NCR, and 4. And we get 1. And so we want to compare these values to the expansion. We got a 1, a 4, a 6, a 4, and a 1. Well, if you look at the expansion of a plus b to the 4th power, look at the coefficients, 1, 4, 6, 4, 1. The exact same coefficients that we got when we did that binomial expansion. Not a coincidence. These are technically considered the way we calculate those individual values in Pascal's triangle if we needed to go one at a time and use the formula instead. So this particular notation, why would we call it in choose R? What does that actually mean? What are we choosing in this case? Well, this particular construct and what it actually means has further reaching implications than just using in the context of a binomial expansion. So essentially what this means in choose R is if you had a set of n items and you want to choose a subset of R, so suppose for instance you had 5 items and you want to choose 2 out of the group, that would be 5 choose 2. And so what this value represents is the number of ways you could take your 5 items and then choose a subset of 2 items. Choose what we call a combination of 2 out of the 5 items. And so there are other applications for this particular notation and what it means. This just happens to be one of the applications for that notation. So this is going to generate what we call binomial coefficients. Again, not surprisingly, because they are the coefficients that we get when we expand a power of a binomial. So this is going to lead us to what we call the binomial theorem, which is going to generalize how we expand any power for any binomial. And it's going to take all those patterns that we recognized on the first page, plus this new notation, and it's going to put it all together into a summation, because notice we're adding up a bunch of terms. Okay, so the binomial theorem. So we're going to allow n to be a positive integer. That's going to be the exponent. The expansion of a plus b to the n power is given by the following. So first off, again, n is a positive integer, so we can't have fractional powers, we can't have negative powers. N has to be a positive integer. Now, notice there are no limitations on what a and b have to be. So those can be anything we want. They can just be a and b. They can have coefficients associated with them. We can look at both rational and irrational numbers. We can even look at complex numbers if we want. In this case, those are completely generic and they can take on any form. So what we want is to generate the expansion of this binomial if we were to raise something to the nth power, which is a completely generic positive integer power. So the general sort of concise way of writing this is going to be the sum, since we're summing up terms, the sum from r is equal to 0 all the way to r is equal to n of the following. So what we'll need first is our n choose r, what we called a binomial coefficient, and that will be followed by a power of a and a power of b. So a per term is going to have the power of n minus r, whatever that happens to be for the specific value of r, and b will have the power of just r, as r increases from 0 up to n. So whatever this comes out to for all the values from r is equal to 0 up to r is equal to n, those will be the terms that we get if we were to expand this binomial. And again, these are going to be the coefficients, what we would otherwise get from Pascal's triangle, that triangle with that pattern that we generated. And then these will be the powers of our individual terms in our binomial. So what would this actually look like if we expand it out and go term by term? Well, we'll start with r is equal to 0. So that will be n choose 0, whatever that happens to be, times a to the n minus r, so n minus 0, which will just be n, times b to the r power. Well, if r is 0, that's just b to the 0 power, which is just 1, so we don't have to write it. plus what we get when r is 1. So that will be n choose 1 times a to the n minus r power, so n minus 1 power, times b to the r power, so b to the first power, plus n choose 2, in other words, allow r to increase to 2, times a to the n minus 2, times b squared, and then we continue in the same fashion all the way down to our last two terms. Well, what would those look like? Well, we go from r is equal to 0 to n, so the next to last term will have a coefficient of n choose n minus 1. Now, here's where the exponents get a little bit more complicated. So it will be a raised to the n minus n minus 1. N minus n minus 1. Well, another way of saying that is a to the first power. So n time, or n minus 1, the n's cancel. We have a double negative on 1, which turns into a positive 1. And then b raised to the r power, which will be n minus 1. And then our last term, we have n choose n. A is raised to the n minus r, so n minus n, which is the 0 power, so that means a goes away. And then b is raised to the r power, which in this case is going to be n. And so that's going to be our expansion. So we see the pattern with how we generate the binomial coefficients. And again, we can just do that in the calculator. The calculator will handle that for us. And then the powers of the first term are decreasing. So we start at the nth power, and then n minus 1, n minus 2, all the way down to 1 and 0. And then the powers of our second term are increasing. So 0 power, in other words, the term isn't there, then the first power, and then squared, all the way up to n minus 1 and n. So essentially this summarizes the most general case we get if we apply all of those patterns that we saw on the first page. So this beats having to manually expand a binomial to a power, because in a lot of cases it's very tedious, it's a very drawn out process, and it's very easy to make mistakes if we're trying to do that by hand. So this is going to save us some time, and it's going to keep us from making those common mistakes. So let's do a couple examples using this formula and the patterns that we see. So we want to expand using the binomial theorem. And we can write out the summation if we want, or we can just use the expanded version recognizing what n is. So we want to expand the binomial 3x squared minus 5y raised to the 5th power. So in other words, in this case, n is equal to 5, and then a is equal to 3x squared, and b, in this case b is negative, so the negative goes with it, so b is going to be negative 5y. So essentially we're applying this formula with these particular values of n, a, and b. So first coefficient, n choose 0. So in our case that's going to be 5 choose 0. And then we're taking our a, our first term, which is 3x squared, and we're raising it to the nth power, which is the 5th power, and we don't see a b in that term. Okay, plus, now we increase our lower value by 1, so plus 5 choose 1. Okay, now we're going to decrease the power on a, so that's going to be 3x squared raised to the 4th power. And we're going to increase the power on b. Well, we didn't see b in the first term because it was raised to the 0 power. Now we're going to see b raised to the 1st power. So times just b as is. Okay, next term, 5 choose 2. Decrease the power on a, so 3x squared cubed. Increase the power on b, so negative 5y squared. Next term, plus 5 choose 3. Okay, Okay, decrease the power on A, so 3x squared squared. Increase the power on B, so negative 5y cubed. And then we're almost there. Automatically we know we need 2 more terms, so we have to allow r to go to 4 and then go to 5 so that the top and the bottom match. So we have 5 choose 4. Decrease the power on A, so that's going to just be 3x squared. And then increase the power on B, so negative 5y to the 4th power. And then our last term, we have 5 choose 5. Decrease the power on A, so it now has a power of 1. We decrease it, it goes to the 0 power, which means it disappears. And then B, we have negative 5y, and we're going to increase the power so that it's 5. And double check your powers. So if we look at the powers of A and B, they should all add up to n for each term that we have. So 5, there's n. Okay, 4 and the understood 1, that adds up to 5. 3 and 2 adds up to 5. 2 and 3 adds up to 5. 1 and 4 adds up to 5, and then 5. So that checks out. And then our values of r increase term to term to go from 5 choose 0 up to 5 choose 5. So now it's just a matter of simplifying all of this down. So we can do one term at a time. We can go ahead and do the binomial coefficients if we want. We are going to see a pattern with the binomial coefficients. Just like there's some symmetry in Pascal's triangle, we're going to see repeats as we continue to generate binomial coefficients. So let's maybe do that first. Actually, no, that's probably a bad idea. Let's just go term by term. So 5 combination 0. That's just going to be 1. Okay, now why is that? Well, remember, this is related to Pascal's triangle, and we noticed in the triangle that all of the outer edges are always going to be 1. So the first one in the sequence is just going to be 1. So 5 choose 0 is going to be 1, and 5 choose 5 will also be 1. So 5 choose 0 is 1. Okay, now we need to apply our exponent to our value of A. So keep in mind, both factors need to be raised to the 5th power. So we have 3 raised to the 5th power, which is going to be 243. And then we also have x squared raised to the 5th power. Now let's review that. So anytime we raise a power to a power, we're going to multiply the exponents together. So that'll be x to the 2 times 5 power, which is x to the 10th power. So that's going to be our first term. Now, next term, 5 choose 1. So 5 choose 1. That's going to be 5. Okay, A raised to the 4th power, so 3 raised to the 4th power, which is going to be 81. And then x squared to the 4th power, so x to the 2 times 4, which is x to the 8th power, times negative 5y, understood exponent of 1, plus 5 choose 2, so 5 choose 2, so 10. Okay, 3 cubed. 3 cubed is 27. X squared cubed, so x to the 6th power. And then careful here, so notice b is negative. Different exponents have a different effect on negatives. So when we take negative 5 and square it, it's going to become positive. So positive 25, and then y squared. Don't forget to square the variable as well. Okay, next term, 5 choose 3. So 5 choose 3. And notice we get 10 again. So as soon as we start to see repeats, that means we've hit the point of symmetry, and that means we're going to see repeated values for the rest of the expansion. So 5 choose 3 is going to be 10, matching this 10, which means we're going to get the matching 5 and the matching 1 as we continue. So let's generate the rest of it. So 3 squared is going to be 9. x squared is x to the 4th, and then negative 5 cubed. Now be careful here, again, the exponent does something specific to the negative. In this case, our exponent is odd, so the result is a negative value. So negative 125, and then that's going to be y cubed as well. And I'm running out of space. So there we go. So negative 125 y cubed. Okay, plus 5 choose 4. And again, we expect to see some symmetry. Let's verify that this one time. So 5 choose 4. And again, as we expect, we get a symmetric value of 5. Okay, times 3x squared times negative 5y to the 4th power. So we're taking negative 5 and we're raising it to the 4th power, which is going to give us 625 times y to the 4th power. And then our last term, 5 choose 5, which will give us a 1. And then we have negative 5 raised to the 5th power, which gives us negative 3,125. And then we have y to the 5th. Okay, so we've taken care of all the binomial coefficients. We've applied all of the exponents. Now we just need to multiply all the factors in each of the terms. So the first term, 1 times 243 times x to the 10th, is going to be 243 times x to the 10th. Okay, next term. Now be careful with your signs. So notice we do have a negative, so it is going to be subtracted. And it's 5 times 81 times negative 5. So 5 times 81 times negative 5. It's going to give us negative 2,025. And then we look at our variables. So we have x to the 8th and we have a y. And in general, we write them in alphabetical order. So x to the 8th first. That's also consistent with what we're seeing in terms of a and b, starting with higher powers of a and working our way down, starting with lower powers of b and then working our way up. Okay, next term. Next term will be positive. So we have 10 times 27 times 25, and so 6,750 times x to the 6th times y squared. Okay, next term. This one has a negative, so it'll be negative again. And we have 10 times 9 times negative 125. Big number, negative 11,250. And then we have x to the 4th and y cubed. Okay, next term, positive. So plus 5 times 3 times 625. So 9,375 times x squared times y to the 4th. And I think I'm going to run out of space, so I'll write the next one on the next line. 1 times negative 3125 y to the 5th. So that'll be a negative term. And we have 3,125 times y to the 5th power. Now, one good thing to check at the very end, make sure you didn't lose a term. So we started with 1, 2, 3, 4, 5, 6 terms. Again, it's going to be n plus 1 terms. And then we have 1, 2, 3, 4, 5, 6 terms. And then 1, 2, 3, 4, 5, 6 terms. So there we go. That is going to be our expansion. That would be a lot of work to find if we had to find it without using the binomial theorem. So even though it is tedious, it requires a lot of detail orientation. This is a time saver versus having to do this by hand. Okay, let's try another one with different values of a and b and a different value of n. So we want to expand x over 2 plus y quantity raised to the third power. So in this case, n is equal to 3, and then a is equal to x over 2, 1/2 x, and then b is equal to y. So automatically, because both of these terms are positive, we know the full expansion is only going to involve addition, and we know based on cubing that we expect to have 4 terms as we expand. So let's write out our coefficients first. So our first coefficient is going to be 3, choose 0, and then we're going to take a, which is x over 2, and raise it to the power of n, which will be cubed. And then b does not appear, so it's b to the 0 power currently. Okay, plus 3, choose 1. Now decrease the exponent on a, so x over 2 squared, and then increase the exponent on b, which means it suddenly appears. So to the first power, this was 0 power, this is the first power. Plus 3, choose 2, decrease the exponent on a, so we go from a square to a first power, and then increase the exponent on b, so that becomes y squared, plus 3, choose 3, and as soon as we get down to n, choose n, same value, then that means that's going to be our last term. So the exponent on a decreases, which means a to the 0 power, it disappears, and then the exponent on b increases, so we get y cubed. Okay, so now let's simplify all of that down. So 3, choose 0. Well, we automatically know that's going to be 1. Based on everything we've seen so far, that's going to be 1. And then we need to cube both the x and the 2. So that's going to be x cubed over 2 cubed, which is 8. And of course, you can verify that in the calculator if you need. Now 3, choose 1. So 3, choose 1 is 3, and that was one of the things we saw with the expansion we previously did using a cube. So that'll be 3, and then x over 2 squared, square the numerator and denominator, so x squared over 4 times y, plus, okay, we're going to see the symmetry now, so once we get to the halfway point, our coefficients are going to be symmetric. So 3, choose 2 will also be 3, and then we have x over 2 raised to the first power, and then y squared. Plus, last term, 3, choose 3, well that's going to be 1. X over 2 disappears, and we just have y cubed. So let's clean it up. Okay, so our first term, just 1 times x cubed over 8, so that's just going to be x cubed over 8. Alternatively, we could write it as 1/8 x cubed if we want. Not a big deal either way. Now the next one, we have a 3 times x squared over 4 times y. So if it helps, think of the 3 as being over 1, think of the y as being over 1, and then we just multiply the numerators and denominators straight across. So that's going to be 3x squared y over 1 times 4 times 1, which is 4. Same kind of thing for the next term. So think of it as 3 over 1. Think of it as y squared over 1. So our numerator is going to be 3 times x times y squared over 1 times 2 times 1, which is 2, plus our last term, which is 1 times y cubed, which is y cubed. So that would be our expansion in that case. So this is what happens when we expand the whole binomial, which of course we certainly do have applications for that. There are certain problems we do where having something in a factored form, something like this, is not ideal, versus having the individual terms in the expanded form. That may make our lives a little bit easier and may make our problems a little bit simpler. So there's also another way we can use the concept behind the binomial theorem. So in some cases, we may not need the entire expansion. In some cases, we may just want to find an individual term, just a single term in the expansion rather than the whole expansion. And so we also have a way to just find one particular term in the expansion that doesn't require us to find all of the terms and then just find it in the series. So we're going to allow n and k to be positive integers where k is less than or equal to n plus 1. So the kth term, think of that as the term in the list of our expansion of a plus b to the n power, is given by the following expression. So its coefficient specifically is going to be n, choose k minus 1. That'll be our coefficient. And then we have a power on a and a power on b. So the power of a is going to be n minus k minus 1. And the power of b is going to be k minus 1. Now, except for the coefficient, there's really nothing special here. This is really just applying what we see in terms of the general form for the binomial theorem. So notice each individual term is going to be n choose r times a to the n minus r times b to the r. Well, in this case, we're just allowing r to be k minus 1. So n minus our value of r, and then b raised to our version of r. So once we know that binomial coefficient, everything else just kind of follows based on the pattern we have from that binomial theorem. So based on that, let's do a couple of examples. So first, we want to find the 8th term of 2x plus y to the 4th quantity raised to the 10th power. In other words, rather than expanding all of this, let's just find the term that would be 8th in the list. So in other words, we want to find the term associated with k is equal to 8. So our value of n is going to be 10. Our value of a is going to be 2x. And our value of b is going to be y to the 4th power. So based on all of this, we have everything we need to find our individual term. So we'll start with our binomial coefficient. So that's going to be n choose k minus 1. So n is 10, and then if k is 8, then k minus 1 is going to be 7. Now once we have our value of n and our value of r, use that value of r and that value of n for our next terms. So it's going to be a raised to the n, which again is 10, minus k minus 1, which is going to be 7, times b raised to the k minus 1, which again in this case will be 7. So now we can just sub in our values. Now first off, what is 10 choose 7? Let's find that. So 10 choose 7 is going to be 120. So that'll be our binomial coefficient, 120. Now a has a value of 2x. So we're then going to have 2x raised to the 10 minus 7, or the 3rd power, times b, which is y to the 4th power, raised to the 7th power. Okay, so let's apply our exponents. So we still have that coefficient of 120. Now we have 2 cubed, which is going to be 8. And then we also cube our x. And then y to the 4th to the 7th power. So we're going to multiply our exponents together, which is going to give us y to the 28th power. And then all we have to do now is multiply our two constants and just clean it up a little bit. So 120 times 8 is going to give us 960. And then we have x cubed, and we have y to the 28th power. So x cubed, y to the 28th. So without having to do the full expansion of this binomial raised to the 10th power, automatically we can just pull this single term out using the formula. So let's try one more with slightly more complicated values, specifically in this case the value of a. So we want to find the fourth term of the expansion of root 3 times x squared plus y cubed quantity raised to the 9th power. So fourth term, that means k is equal to 4. And then based on our binomial and our power, we know that n is equal to 9, a is equal to root 3 times x squared. Now be careful when you write this. So 3 is under the radical, x squared is not. So we have the square root of 3 as a coefficient for x squared. Okay, and then b is equal to y cubed. So what is our fourth term? So it's going to be n, choose k minus 1, so n is 9. Choose k minus 1, well if k is 4, k minus 1 is going to be 3. So that means we're going to use 9 and 3 as we generate our exponents. So that's going to be 9 choose 3 times a to the 9 minus k minus 1, 9 minus 3, times b to the k minus 1, so b cubed. So now we just need to plug in our values, simplify things down. So let's find 9, choose 3, our coefficient. That's going to be 84. Okay, and then we'll plug in our a, we'll plug in our b. So a is going to be the square root of 3 times x squared, and that is now being raised to the 9 minus 3, or the 6th power. And then b is y cubed, and that is also being cubed. Now the perceivably hard part here is dealing with that radical. But you have a calculator. The calculator can help you. I'll also show you how to do this without using a calculator, because in some cases, some powers applied to a radical are not easily simplified in a calculator. So we'll deal with that as we come to it. So we have 84. Okay, now for this next one, I want to sort of write it out separately, and again, we'll go back and we'll look at that radical individually. So we have to take the square root of 3, and we have to raise that to the 6th power. And then we also have to take x squared and raise it to the 6th power. Now that part we can do. So we're just going to multiply the power by the power. So that's going to be x to the 12th power. And then y cubed is going to be y to the 9th power. Now root 3 to the 6th power. Let's deal with that by itself. So the square root of 3 raised to the 6th power. Here's how I like to think of this. Now first off, let's see what happens if we just plug it into the calculator. So if we take the square root of 3 and raise it to the 6th power, we get 27. Now why do we get 27? And why would I need to work this out by hand if the calculator did it for me? Well, this works out nicely in the calculator because we have an even exponent. If we don't have an even exponent, then simplifying this in the calculator is not going to be a good idea because it is going to give you an irrational number. Okay, so how do we deal with this in light of any situation? Well, what I want to think of this now is as something squared and then another power. So we're raising the square root to the 6th power. I want to break that 6 down into two components. So I want to think of it as the square root of 3 squared. Now why is that helpful? Well, if we square that square root, we know it's going to rationalize it. But using this rule that we've applied a couple times already, but using it backwards, what would the additional exponent have to be in order to be equivalent to a power of 6? Well, if we're already squaring it and we want something that would generate a power of 6, then we would also need to cube that result. So let's check it. So if we were to square it and then cube it, multiply the exponents, and that gives us a result of 6. And so then we can square our square root, which again, that rationalizes it. So that's going to give us a 3, and then that's going to be a 3 cubed, which simplifies down to 27. Now, just for the sake of working it out, it's completely out of the context of this problem, but just to be sure in case you encounter this. What if we had something like the square root of 3 raised to the 5th power. How would we handle something like that? Well, first off, what happens if you put it into the calculator? Okay, so if we were to take the square root of 3 and raise it to the 5th power, notice we get a decimal. That's just an approximation because that's really an irrational number. So I'm going to handle this in a similar but slightly altered way. So I like relating my square root to even exponents because I know I can write that even exponent as something squared then to another power. I can do something similar here with one additional step. So root 3 to the 5th power would be the same thing as the square root of 3 times the square root of 3 raised to the 4th power. So I'm just pulling off one factor of root 3 and then I'm writing what I'm left with. So the benefit of doing that is, yes, we have a square root of 3, which is irrational, but what's left over is now a square root to an even power, and so essentially what we did right here, we could now do with the square root of 3 to the 4th power. This other root 3 just kind of hangs out. So we have the square root of 3 times root 3 to the 4th power, which again, if we break it down the same way we just did, that would be the square root of 3 squared, and then we would square that result, hence generating the 4th power. So the square root of 3 squared would be 3, and then if we took the 3 and squared it, we would get a 9. So the result of this would be 9 root 3. And we can verify that that's correct. If we were to take 9 root 3 and plug it in, well, notice we get the same approximation. So root 3 to the 5th and 9 root 3 truly are the same thing. So this would be the approach you'd want to take if you want to simplify something where you have a radical and there's an odd power, and so the result is actually irrational. So completely a side note, but just worth mentioning in case you run into that with this kind of problem. So let's get back to our actual problem. So we had root 3 to the 6th, which is 27. So we have 84 times 27, and that's going to be our coefficient. So that is 2,268, and then we have x to the 12th power and y to the 9th power. And so that would be the 4th term in this particular expansion if we were to write out the whole expansion. So the binomial theorem is very helpful. It's very much a shortcut that's going to save you a lot of time if you have to expand a binomial raised to a power. So we can use it to get the entire expansion if that is the goal, and we can also use the strategy we just looked at to pick out individual terms in the series.